You are falling, not into water, not into fire, into a region of space-time so extreme that nothing, not even light, can escape once it crosses a single boundary, a black hole. In the next 10 minutes, we take the most accurate scientific journey possible into one. What you would actually see, what happens to your body, and why the universe itself begins to rewrite the rules around you. Black holes come in different sizes. A stellar mass black hole, the remnant of a collapsed star, is only a few kilometers across. Fall toward one of those, and the difference in gravity between your head and your feet becomes lethal long before you reach the event horizon. You are torn apart by tidal forces in a process called spaghettification. But choose a supermassive black hole, millions of times the mass of our Sun, like the one at the center of the Milky Way. And the event horizon is so large that the tidal gradient at its surface is relatively gentle. You can cross the point of no return still in one piece for a while. From a safe distance, a black hole is invisible. We detect it only by the way it warps light and by the glowing disk of matter swirling around it. That matter is swirling around it at nearly the speed of light. That disk can reach millions of degrees. As you approach, the sky begins to change. Light from stars behind the black hole is bent around it. You see multiple images of the same stars. The entire universe starts to look like a distorted funhouse mirror. Closer still, you reach the photon sphere, the last place where light can orbit in unstable circles. Here, if you looked sideways, light wrapping completely around could show you the back of your own head. The black hole now fills half your vision. To a distant observer watching you, something strange is already beginning. Your image slows down. Your light redshifts toward the infrared and beyond. Eventually, you appear to freeze just outside the horizon, fading into invisibility. But from your perspective, the story is very different. You cross the event horizon. There is no wall, no explosion. For a supermassive black hole, the curvature is gentle enough that you notice nothing special at the moment of crossing. Light from the outside universe can still reach you, it just can never leave. Behind you, the entire outside universe compresses into an ever smaller bright circle. Ahead, every direction leads inward. There is no up anymore. Escape is now mathematically impossible. Even light itself is trapped. Now time and space begin to reveal their true nature. To the outside universe, you are frozen at the horizon forever. But your own clock continues normally. In your proper time, you fall inward rapidly. The difference in gravitational pull between your feet and your head grows. This is the same tidal force that creates ocean tides on Earth, only now it is extreme. Your body begins to stretch lengthwise while being compressed from the sides. The process is called spaghettification. For a stellar mass black hole, it would have already killed you. For a supermassive one, it is only now becoming dangerous. The stretching accelerates. Your feet feel a stronger pull than your head. The difference grows until it exceeds the strength of the bonds holding your body together. Bones, organs, even individual cells are pulled apart. The process happens faster than pain. In the NASA simulation of a Sagittarius A star-like black hole, destruction occurs roughly 12 to 13 seconds after crossing, 99% to the center. You are no longer a person. You are a stream of particles following the curvature of space-time. What remains of you reaches the singularity. In classical general relativity, this is a point of infinite density and infinite curvature, where space-time itself ends. All paths terminate here. The laws of physics as we currently understand them simply stop working. We do not know what actually happens. Quantum gravity, a theory that does not yet exist in complete form, will almost certainly change the picture. Some models suggest a surface-like region, a bounce, or a remnant. Others preserve the information that fell in. Right now, honesty requires us to say, we do not know. Even the black hole is not eternal. Stephen Hawking showed that black holes slowly radiate energy, Hawking radiation, and will eventually evaporate completely. For a stellar mass black hole, this takes an unimaginable 10 to the 67th years. For a supermassive one, the timescale is vastly longer still. What happens to the information that fell in remains one of the deepest unsolved problems in physics. The information paradox. Does it re-emerge in the radiation? Is it preserved in some other way? We do not yet have the answer. Falling into a black hole is no fiction. It is a real journey through the most extreme environment the universe allows. You would see the sky warp and time distort. The fabric of reality stretches until the known laws fail. Remember, somewhere out there, matter is crossing an event horizon right now. And the universe is still keeping some of its deepest secrets. If this journey changed how you see black holes, share it.